Hello, and welcome back to From Zero to Zeta. I'm your host, Rowan McKee. Before we get started, just a few quick reminders. If you've been enjoying this series, please take a moment to like the video and subscribe to the channel. It really helps the channel grow and makes it possible for me to keep producing more content like this. And if you'd like to ask questions, compare notes, or get help with the exercise at the end of this episode, join our community Discord server. The link is in the description below. In today's episode, we're going to continue our study of groups by answering three big questions. How do the sizes of subgroups relate to the size of the whole group? Which subgroups behave well enough to allow us to build quotient groups? And how are these special subgroups connected to homomorphisms, the structure-preserving maps between groups? We'll begin with one of the first major theorems in group theory, Lagrange's theorem. Then we'll introduce the idea of normal subgroups and see why they matter. Finally, we'll define homomorphisms and kernels and prove that normal subgroups are exactly the kernels of homomorphisms. This is the key turning point in our group theory series. We'll be connecting the internal structure of a group with the external maps between groups, setting the stage for even deeper results later on. Let's get started. Last time we explored the idea of equivalence relations and how they lead naturally to cosets. If H is a subgroup of a group G, then H partitions G into neat disjoint slices called cosets. We asked the natural question, can we make those cosets into a group of their own? In some cases, the answer was yes. For the integers modulo n, coset addition gave us exactly the modular arithmetic we already knew. Clean, simple, and satisfying. But not always. In the Rubik's Cube, we looked at the subgroup generated by turning just the right face. The cosets were fine, but when we tried to multiply them, the results depended on which representative we chose. That meant the operation wasn't well defined. In other words, the whole structure broke down. We also played with concrete subgroups of Z12. For example, the subgroup 06 split Z12 into pairs, while 048 split it into triples. In every case, the cosets were the same size and tiled the whole group perfectly. Finally, I gave you some homework. Cosets in S4, the group of all permutations of four objects. If you tried it, you saw that once again the cosets partitioned S4 evenly, but when you tried to multiply them, things didn't quite behave the way we'd want for a proper group. So we ended with a puzzle. Which subgroups behave well enough to let us form quotient groups? That's exactly the question we're going to start answering today. Before we can answer that question, however, let's go over something I hinted at last time. This time more formally, Lagrange's theorem. If H is a subgroup of a finite group G, then the size of H divides the size of G. In symbols, H divides G. The idea is actually simple but powerful. Every element of G belongs to exactly one coset of H. That means the cosets of H partition the whole group G. Each coset has the same size as H itself, because if you map H to GH for a fixed G, that map is a perfect one-to-one correspondence between H and GH. So G is made up of some number of these cosets, all of equal size. That means the cardinality of G is equal to the number of cosets times the cardinality of H, and therefore the cardinality of H divides the cardinality of G, QED. Let's look at some examples. In Z12, the subgroup 06 has order 2. The subgroup 048 has order 3, and the subgroup 0369 has order 4. Each one divides 12 exactly, as Lagrange's theorem guarantees. In S4, the group of all permutations of 4 objects, the group has order 24. So any subgroup of S4 must have an order that divides 24. That means subgroup orders can only be 1, 2, 3, 4, 6, 8, 12, or 24. Lagrange's theorem gives us a powerful tool for reasoning about group size. It doesn't tell us which subgroups exist, but it does tell us which subgroup sizes are even possible. We'll keep this in mind as we move forward because it will help us understand why some subgroups behave nicely while others don't. We're trying to solve the following problem. When do coset operations behave well enough that we can form a quotient group? First, let's start with what we already know. In abelian groups, coset operations always seems to work. Take Z under addition and the subgroups 3Z, the cosets are 3Z, 1 plus 3Z, and 2 plus 3Z. If we add two cosets, no matter which representatives we pick, we always land in another coset. For example, 1 plus 3z plus 2 plus 3z is 3 plus 3z, which equals 0 plus 3z. We know that an abelian group implies that the coset operation is well defined. If we let G be abelian and H be a subgroup of G for A prime B prime with A prime and AH and B prime and BH, we may write A prime equals AH1 and B prime equals BH2 with H1, H2 in H. Then A prime B prime equals AH1 times BH2, which, because it's abelian, equals AB times H1, H2, which is an element of the coset ABH. AH times BH equals ABH independently of representatives. Thus, in abelian groups, coset multiplication is well defined. This suggests a conjecture. Coset operations are well defined if and only if the group is abelian. We just confirmed one direction. To test the converse, we move to a non-abelian setting and ask, can a non-abelian group still have a subgroup whose cosets multiply well-definedly? Definition. The symmetric group Sn is the group of all permutations of n objects. The operation of it is composition of permutations. Consider S4. Take H equals E1, 2. If we form cosets of H and try to multiply them, we quickly run into trouble. The coset 1, 3H contains both 1, 1, 3 and 1, 3, 2, and using different representatives can send the product to different cosets. So here the coset product is not well defined. That shows some subgroups in a non-abelian group misbehave, but it does not yet answer our question. Could there be a subgroup in a non-abelian group that does behave well? To get there, we need a couple of important observations. First, every permutation can be broken down into simple swaps of two elements, called transpositions. A transposition is a permutation in Sn that swaps two elements and fixes the rest. Why do transpositions generate all of Sn? Think of a deck of cards. To rearrange the deck into any order, you can take a card and swap it into the position where it belongs. Doing this repeatedly, one swap at a time, you can reach any possible arrangement. That's why every permutation can be expressed as a product of transpositions. Now, here's the key observation. Every permutation falls into one of two categories. It can be written using an even number of transpositions or an odd number of transpositions, and this distinction is consistent. Parity fact. Every permutation is either always even or always odd. No permutation can be written both ways. Suppose a permutation sigma could be written in two different ways. Once as a product of k transpositions, and again as a product of L transpositions, with k even and L odd. Now take the inverse of the first decomposition. Since every transposition is its own inverse, the inverse of a product of k transpositions is also a product of k transpositions, just in the reverse order. Composing this inverse with the second decomposition gives an expression for the identity permutation as a product of k plus L transpositions. But if k is even and L is odd, then k plus L is odd. That would mean the identity itself could be written as an odd number of transpositions. The identity does nothing, so it corresponds to 0 transpositions, which is even. Contradiction. Therefore, parity is well defined. Definition. The alternating group An is the subgroup of Sn consisting of all even permutations. In S4, there are 24 permutations. Exactly 12 are even, so the cardinality of A4 is 12. The two cosets of A4 in S. We now describe explicitly the two cosets that make up S4 divided by A4. The even coset, which is A4 itself, is here. The odd coset, the complement of A4, is here. There are 6 transpositions and 6 4 cycles, both are odd. We now compute the left coset 1, 2 times A4 to verify it equals the set of all odd permutations we listed before. Composition is right to left. With the 4 double transpositions, we've got this set of products. With the 8 3 cycles, these. Putting all this together, we do in fact get all of the odd permutations. So multiplying the even coset by a single transposition produces exactly the odd coset. An even permutation has an even number of transpositions in any decomposition. Left multiplying by single transposition adds one swap, changing even to odd. Thus 1, 2 times even is always odd. Since the cardinality of A4 is the cardinality of the odd cosets, that is 12. And left multiplication by 1, 2 is a bijection. 1, 2 times A4 must be the entire odd coset. Having identified the two cosets explicitly, we can display their multiplication at the coset level. Here it is. This table shows that coset multiplication in S4 with respect to A4 is well defined. No matter which representatives you pick from each coset, the product lands in the same coset. At the same time, inside the odd coset, the elements do not commute. 1, 2 times 1, 3 is not the same as 1, 3 times 1, 2, so the ambient group S4 is not abelian. The point is that well-defined coset arithmetic does not require G to be abelian. It requires the right kind of subgroup. This leads to the concept we've been building toward. Definition: a subgroup H of a group G is normal, written H triangle equal to G, if for every G in G, GH G inverse equals H. Equivalently, the left cosets of H equal its right cosets. And here's another definition. Given Gx in G, the conjugate of x by G is G inverse xg. The process x maps to G inverse xg is conjugation. Normal subgroups are precisely the subgroups for which coset multiplication is well defined. They are the ones that make quotient groups possible. So far, we've been studying a group's internal structure, cosets, normal subgroups, and quotient groups. Now it's time to shift perspective and ask, how do groups relate to one another through maps? Earlier, we teased the idea of an isomorphism, a bijection between groups that preserves the operation, showing that two groups are the same in structure. If we relax the bijection requirement and only ask that the operation be preserved, we get the broader notion of a homomorphism. Definition: a function phi goes from G to K between groups is a homomorphism if for all A and B in G, we have phi of AB equals phi of A times phi of B. This means multiply first in G or map each element to K and multiply there. Either way, the result is the same. Let's work through some concrete examples. Example 1, we have reduction mod 12. Define phi from z to z12 by phi of n equals n mod 12. If we add two integers first, then reduce mod 12, we get the same result as reducing each one mod 12 and then adding in z12. For instance, phi of 8 plus 15 equals 23 mod 12 equals 11. Equals phi of 8 plus phi of 15 equals 8 plus 3 equals 11. So phi is a homomorphism. Example 2, we have a scenario we haven't quite covered before, but it should be familiar enough. This is called a factor group, a factor map, when one modulus divides another. Define psi going from z12 to z4 as psi of n mod 12 equals n mod 4. This is well defined because 4 divides 12. For example, psi of 7 mod 12 equals 7 mod 4 equals 3. And psi of 11 mod 12 equals 11 mod 4 equals 3. And checking the homomorphism property, psi of 7 plus 11 mod 12 equals 18 mod 4 equals 2. And psi of 7 mod 12 plus psi of 11 mod 12 equals 3 plus 3 mod 4, which equals 2. So psi is a homomorphism. And example 3, we're dealing with an infinite set, so a scaling map to the even integers. Define delta from z to 2z by delta of n equals 2n. Then delta of m plus n equals 2 times m plus n equals 2m plus 2n equals delta of m plus delta of n. So delta is a homomorphism from the integers onto the even integers. This example shows a map into a substantial infinite codomain that still respects the group operation. Our last example is exponentiation into S4. Define theta from z to S4 by theta of n equals the permutation 1, 2, 3 to the nth power, where 1, 2, 3 is this 3-cycle permutation in S4. Then theta of m plus n equals 1, 2, 3 to the m plus n, which equals 1, 2, 3 to the m times 1, 2, 3 to the n, which equals theta of m times theta of n. This exponentiation works because this forms a cyclic subgroup. So theta is a homomorphism. Its image is a cyclic subgroup E123,132 of S4, showing how a simple infinite group like Z can map neatly into a finite permutation group. These examples illustrate the variety of homomorphisms: reduction maps that collapse structure, factor maps when one modulus divides another, scaling maps into infinite codomains, and maps from simple cyclic groups into non-abelian permutation groups. Each preserves the group operation, and each will give us new tools for connecting the idea of normal subgroups with the kernels of homomorphisms. We've seen how homomorphisms preserve structure, but what happens when they're not one-to-one? When multiple elements of the domain collapse to the same output? If a homomorphism phi from G to K were injective, each element of G would map to a unique element of K. When it isn't injective, groups of elements in G share the same image in K. Each of these groups of elements acts identically once viewed through the map phi. Let's look at a few concrete examples. The first example, if we let phi go from Z to Z3 be defined as phi of n equals n mod 3, this map wraps the entire number line around into 3 repeating buckets: the 0 bucket, the 1 bucket, the 2 bucket. Each set is the complete preimage of one element in Z3. Addition respects these sets. Adding something from the 1 set to something from the 2 set lands you back in the 0 set. Among them, the 0 set is special. It contains all multiples of 3, the integers that map to 0 in the codomain. Example 2, we have psi goes from Z12 to Z4. This map respects addition and is well defined because 4 divides 12. The domain Z12 splits into 4 sets. Each of these sets maps to one element of Z4. In this case, the clock with 12 hours wraps onto one with 4 hours, where each position on the smaller clock represents every third position on the larger one. The 0 set 048 is special. It's the collection of elements in Z12 that map to 0 in Z4. Our next example is collapsing a product group. Consider alpha going from the Cartesian product Z cross Z to Z, defined by A of Mn equals m plus n. This map takes a grid of integer pairs and projects it onto the number line by adding the coordinates. Different pairs can yield the same sum, so alpha is not injective. For example, 2, 3, 1, 4, 0, 5, negative 1, 6 all map to 5. Each preimage of a number k in Z forms a diagonal line, Mn, such that m plus n equals k. The diagonal passing through 0, 0, all pairs m, negative m, maps to 0 and will be the one to watch. We know from earlier that the set of even permutations, A4, forms a normal subgroup of S4. This means that we can organize S4 into 2 big sets, one containing all even permutations and one containing all odd ones. Let's take advantage of that and define a function phi S4 to Z4. By phi of G equals 0 if G is even, 1 if G is odd. In other words, phi keeps track of the permutation parity. To see that phi is a homomorphism, notice that when we multiply 2 permutations together, their parities add modulo 2. Even composed with even is even, odd composed with odd is even, and mixing even with odd gives odd. This matches the addition table in Z2 perfectly, so phi is a homomorphism. The function phi is not injective, because there are many distinct even permutations and many distinct odd ones that map to the same value. The elements that map to 0, the even permutations, form the subgroup A4. Those that map to 1 are the odd ones, which together form the other coset of A4 in S4. In every one of these examples, we saw the same pattern. A non-injective homomorphism takes its domain and divides it into distinct classes, where each class behaves the same way under the map. And among those, there's always one that maps to the identity element of the codomain. So we have this definition. The kernel of a homomorphism phi from G to K is the set ker of phi equals G in G, such that phi of G equals the identity element in K. In Other words, the kernel is a collection of elements that become invisible under the map, the ones that land on the identity in the codomain. Today we explored what happens when a homomorphism isn't one-to-one. We saw that when you apply a homomorphism to a group, different elements can collapse together. They can share the same output in the codomain. This collapsing naturally divides the domain into classes of elements that all behave the same way under the map. Among those classes, one stands out, the set of all elements that map to the identity in the codomain. That special set is what we call the kernel. Through several examples, we saw how kernels behave. In Z to Z3, the kernel is 3Z, all multiples of 3. In Z12 to Z4, it's 0, 4, 8. In Z cross Z to Z, it's the diagonal M, negative M. And in S4 to Z2, it's the even permutations A4. In every case, the kernel wasn't just a random collection of elements, it had structure. Each one was closed under the group operation, and each one stayed stable when we took inverses. That means kernels always form subgroups of their domain, and as we'll see in the next episode, they're not just any subgroups. They're the special ones we call normal subgroups. Next time, we'll take all of this intuition and turn it into a formal foundation. We'll move to the whiteboard and carefully prove 4 core theorems. The kernel of any homomorphism is a subgroup of the domain. The image of any homomorphism is a subgroup of the codomain. The subgroup is normal if and only if it is the kernel of some homomorphism. And finally, the First Isomorphism Theorem, which shows that G, quotient, cur phi, and image phi are really the same group wearing different labels. Those proofs will complete the picture, showing how the invisible parts of a homomorphism, its kernel, and the visible parts, its image, fit together into one of the most beautiful relationships in all of group theory. Before moving on to the next episode, take a few minutes to work through these exercises. You may want to pause between each exercise. They're meant to help you test the ideas we covered today and make sure you really understand how kernels and normal subgroups start to appear naturally in homomorphisms. The first exercise is, in Z6, list all of its subgroups and decide which ones are normal. Hint, remember that Z6 is abelian, so this one shouldn't be too bad. The second one, use Lagrange's theorem to explain why Z6 has no subgroup of order 4. Think about what Lagrange's theorem tells you about the possible sizes of subgroups. Third exercise, construct the map pi from Z to Z quotient 4Z. Pi of n equals n mod 4, and identify its kernel. What kind of integers are sent to 0 in the codomain. If you can reason through these, you've got a solid understanding of how homomorphisms divide a group into structured layers, the foundation you'll need for the proofs coming next time. If you enjoyed this episode, please take a moment to like it and subscribe to the channel. It really helps more people find these lessons and keeps the series going. If you got questions, examples of your own, or thoughts about what clicked for you today, leave a comment below. I love seeing how you all think about these ideas, and your questions often inspire future episodes. For more discussion, come join the From Zero to Zeta Discord server. It's a relaxed space for asking questions, working through exercises, and talking math with others who are following along. You'll find the invite link in the description. And if you'd like to hang out live, I also stream occasionally on Twitch under the name From Zero to Zeta, where I host live drop-in tutoring sessions, and also under the name Zero to Zeta Gaming, where I play chess games and analyze it live on stream. Thanks for watching, and I'll see you in the next episode.